When we looked at visualization, we talked a bit about control variables and confounding factors. So we used first bivariate visualizations to look at the relationship between two variables, and then we looked at multivariate graphs to add control variables to see whether on the categories of those control variables the relationship between the original independent and dependent variables still hold. In regression analysis we do the same quite often. So rather than looking at the relationship between x and y, we tend to have regressions where we have multiple x's. So you have beta 1 as the intercept, beta 2 times x1, beta 3 times x2, and so forth. So we can add multiple variables to the same linear regression. And everything I said about residuals, error terms, the naming of x and y, it all still holds. The one difference is that it becomes harder to visualize. Whereas with one independent variable and one dependent variable we can plot it as a regular scatter plot. When you have two independent variables it becomes a three-dimensional picture and so forth. So here on this slide you see an example with two x variables and therefore a three-dimensional picture, and we're looking at a plane, not a line. So it becomes harder to visualize, but everything else is still true. So all these points are still a certain vertical distance away from this plane, and those are the residuals. And we can still look at the predicted value of y given the estimated coefficients for beta 1, beta 2, beta 3. Or sometimes we will write the intercept as beta 0 and then beta 1 for x1 and so forth. So typically we use this in the social sciences to add control variables. When you're interested in causal inference, when you're trying to explain y by looking at x, we tend to use multiple regression to add control variables to see if the relationship between the original x and y still hold. In more machine learning applications, we tend to be more interested in prediction, less in causal inference. So there is no such thing as a control variable, but we often can predict better if we have more variables. If we know more about an individual, we can predict their behavior better. So adding more variables will lead to more accurate predictions, typically. So when you run a regression or when you see a regression published in an article, you will often see a table like this. You will see a set of independent variables, and with each of them there is a coefficient. So for example here, immigration econ captures the extent to which respondents think immigrants are good for the economy, and this positive number 1 suggests that there is a positive relationship between thinking immigrants are good for the economy and being in favor of European integration. Age is a second variable, and this negative coefficient suggests that there is a negative relationship. Younger people are more in favor of European integration than older people on average. Gender male suggests that men are less in favor of European integration than women, because it's a negative coefficient, and so forth. The numbers between parentheses you can ignore for now. They are relevant in any econometrics or statistics application, but in this course we are not so concerned with that. They capture the level of uncertainty around all our estimates. So while regression is normally for continuous variables, there is actually one exception. We can add dummy variables. Dummy variables are variables with only two categories, male, female, voter, non-voter, and so forth. But they have to be coded as a 1 and a 0. One of the two categories has to be 1, the other category has to be 0. And if you want to make your regression tables a little bit easier to read, you always name the variable after the 1 category. So if I code gender as being 1 male, 0 female, then I can add it as a regression, and then it helps to call it male rather than gender. The interpretation changes a little bit. Where the original beta coefficient tells you how much does y increase when x increases by 1. In the case of a dummy variable, we are talking about different intercepts. We are talking about different points where the line crosses the y-axis. So when we have a regression with some variable x but also some dummy variable, then we get two parallel lines, the slope given by the coefficient on x, and the distance between those two lines vertically denoted by the coefficient on the dummy variable. So here we have two parallel lines. How steep they are is captured by beta 2. When d is 0, beta 1 is the point where this line crosses the y-axis. And when d is 1, then it crosses the y-axis at beta 1 plus beta 3. So two parallel lines, and beta 3 captures the difference between those two lines. So when a nominal variable has two categories, male, female, voter, non-voter, protester, non-protester, and so forth, democracy, non-democracy, we can capture it with a dummy variable, 0 and 1. But when a categorical variable has multiple categories, this of course becomes more difficult. However, it's still straightforward to add it to a regression. We can simply create dummy variables for each category. If we take how did you vote in the last election from, for example, the INES data, then we can say if they said Fianna Fáil, then the Fianna Fáil dummy is 1 when this voter voted Fianna Fáil and 0 otherwise. When the respondent answered Sinn Féin, then we have a second dummy, Sinn Féin dummy, and that one will be 1 for all Sinn Féin voters and 0 otherwise, and so forth. So one categorical variable with multiple categories becomes a set of separate dummy variables, 1 for each category, that is 1 for all respondents that chose that category and 0 otherwise. And then we can add each of those separately to the regression and interpret them all as different intercepts. One slight caution, you can only add for each category -1, you can add the dummy variable to the regression. So if there's 5 categories in a variable, you can create 4 dummy variables that you add to the regression. And all the coefficients represent the difference between that category and the category you left out. So if I have a dummy variable for Fianna Fáil voters, 1 for Sinn Féin voters, 1 for Green Party voters, 1 for Fine Gael voters, then I can, for example, leave the Fianna Fáil dummy out and put the other 3 in the regression. And then the coefficient for the Sinn Féin dummy captures how much more or less Sinn Féin voters say support EU integration than Fianna Fáil voters. So it's always relative to the category you left out.